to stress in this course. So this lecture is kind of going about lab 15, 16 and onwards. So this lecture covers some of the material that we are experiencing from lab 15, 16 and onwards, okay? If you have any questions, like you can interrupt me and ask questions directly. So I will share also with the online people. All right. So what is this lecture is about? I mean, the whole course is about trying to convey the message that programming is not a single uniform activity. It has some stages, and the coding stage is the actual boring and kind of not that exciting stage. And the fun part is what happens in your head before you start coding. So the talk is about this part and like why it is important and why we have this course at all. So we've been discussing it from the beginning that we sort of dealing with different levels of abstractions, and coding is kind of getting to a level of abstraction which is understandable by the computer. So like coding is one of those abstraction layers where you're expressing things to something that from that level down can be mapped to the machine code, right? So we're expressing an abstraction layer in a language, programming language or scripting language or whatever that is taken up by a compiler or interpreter or something that then automatically gets to the machine. But in between, there are different levels as well. And on top of that, there are different levels as well, right? So now this lecture is a little bit what happens above that, before you have the code which the compiler can take. So coding is turning your made decisions into something, into syntax that can be taken up by the machine. And programming is the conceptualization which happens before that. You have to plan what you need to turn into syntax, right? And that turning into syntax, that's really nicely taken care of by AI these days. Most of us don't have to do that manually anymore. What AIs are not that great at is this one, is the conceptualization phase. They will do things for you. They will kind of come up with concepts and with type systems and with solutions. But most of the time, it's kind of either smelly or kind of not quite right. That part is pretty good. With this part, the AI tools, the generative AI tools are quite good, and they can help you to do that part very well. But to do this part, you have to do this part. So the coding part always was kind of easy. I know it's hard for you to believe because you are kind of learning to code first, and coding seems like an obstacle, but coding is not that hard unless you're coding in JavaScript, which is a nightmare, right? So I mean, it is not that easy neither. Like coding in itself is an art. It's like you have to be able to do that, but it's much more constrained problem to what happens before that. So if you already know all the conceptualizations, the coding is quite mechanical. So that part is a little bit more mechanical, the coding part. The programming part, we cannot automate it. Like it has to happen in a brain kind of, and in between the brains, between your brain and the brain of the person who needs your software. So that is much harder part. All right, so before a single line is typed, what we have to design is what should exist, what will actually exist in this abstract space. So what concepts deserve a representation? What is the semantics behind those symbols, like what they will mean? What are the rules? What will be invariant? What will change? What is possible? What is not possible? And then you have to kind of think about the layering. Like you have to plan what those abstraction layers are and how they interplay with one another and how they operate, right? So after you've done all this work, the code is like the result of all your decisions. So it follows mechanically from the decisions that you've made, right? So if you need a socket, you have to design like what sort of pattern, like how can we interact with it? Is it going, is it possible for me to request something and then request again? Or if I requested something, I cannot request again. I have to wait for response. All those patterns are for you to decide. And then, you are making those decisions. So what type system do you use? What concepts do I have represented? What attributes do they have? What is named? What is not named? What are the static and dynamic semantics of the concepts? All of this has to happen, and it happens before you do the coding, right? It's not a waterfall. We are doing it iteratively. Sometimes we conceptualize something, we try to code it, and then we feel, no, it's quite not right. We go back and conceptualize it again, and we kind of do a loop. But certain things happen in your head before you type, right? So this is the talk today. We kind of touch a magic box, look, raw bytes. And then we will talk about 0MQ. That was the lab 15. We will talk about Redis a little bit. And then we'll talk about type system, entity component systems, and domain-specific languages. DSL stands for domain-specific language. And it is a language that defines certain things for you. And it can be a self-contained language, kind of like a programming language, but every time you define your types and your functions and your variables, you are creating a new language which you will use to achieve something, right? So if you import the library creates a certain API, certain concepts, and then you're gonna use it. And those concepts, those library artifacts are kind of creating a language that you are using. So DSL is not necessarily just something that you have to have a parser for. It can be all those constructs that you constructed yourself to be able to solve the problem, right? So you're building kind of a certain vocabulary, certain type system, and then you're using it. And by building it, you kind of creating this DSL. So we sort of gonna traverse this this hierarchy. So we start with 0MQ, the communication contracts, right? So at the bottom, we just have a byte stream, and it's bidirectional. So you can send bytes one way and send bytes back, right? That's what we have on the abstraction layer, all the way down. We sort of saying, yeah, there is some sort of network stack. It's a black box for us. We can send bytes this way and get bytes back, right? And we have to have some sort of patterns. So we have to decide, who sends messages to whom, when is the beginning and when is the end of the communication, who can speak first, who cannot speak first. And then once you speak first, can you speak again or do you have to wait? You have to decide all those patterns, right? So that happens on the conceptual level. You're sort of saying, okay, I need to have those active components and they have to behave in a certain way, right? So 0MQ is an abstraction layer, is a library which helps you to make the decisions and also helps you to implement them because it creates for you reusable components. It creates for you reusable artifacts or abstractions that you can reuse, right? So you don't have to invent everything from zero. You can kind of say, yeah, like what I need fits into that pattern. I can use it, right? So you're basically choosing the patterns, and this is programming. So you're saying, yep, I'm choosing this pattern, right? And then if you decided that you're using this pattern, there is a special call or special API that you kind of invoke, right? So what pattern 0MQ offers to us? One of the simplest patterns it offers is called request reply. And the request reply has two active components, two endpoints, which one is called client, the other one is called server. It's an abstraction. Of course, in your case, it could be a client and the broker if you're doing the chat thing, or you could call it differently, but the roles are client and the server. And then the client requests something from the server, and then the server has to reply. The client cannot request multiple things. The client has to request one thing and wait, cannot request again. If the client requests again, that's an error because it didn't got a response yet. So the client requests one thing and then the server will reply. And that's the protocol. That's the agreement that we're saying it's going to happen. That's the pattern that ZeroMQ offers to us. It's built in. And we can say, yep, we want a use case where that is the case. We want to request something and then we want to get a response, right? What do you give up? Well, you give up this ability that if you have a slow server and you have multiple requests, it will kind of wait because it has to handle them sequentially, right? So you cannot have things done concurrently. You have to do everything in sequence. Request, response, right? Sometimes that's what we want. Sometimes that's not what we want. So if we want this, that's great. If we don't, we have to move to something else. So what if you want to send something to multiple clients, right? Okay, there is another pattern. This pattern is called publish subscribe. It has a single broker which broadcasts the same message to everybody, and then the subscribers subscribe to a particular topic and they get values for that topic, right? So the message is broadcasted to everybody, but the subscribers, the clients, they pick what they subscribe into. So in this particular scenario, there is a kind of a convention for specifying the topics, and it is like chat room A. And then if you say chat room A, you're gonna get all the advertisements which get to chat room A. If you subscribe to chat, you're gonna get all the advertisements which go to all the chats, which have that prefix, right? So you're gonna listen to all the rooms. And then client A and C only listen to room A. They ignore all the other rooms, and client B listens to everything, right? A nice publisher broadcast pattern, very useful, very typical. And what you give up? Well, you give up that nobody confirms that they've got it, right? So if you really need confirmations, that pattern might not be for you. But if you don't care about the confirmations, that's perfect. What other thing you're giving up here? Well, everybody listens to everything. You cannot restrict who gets what. So if I have one publication and 1,000 clients, I will have 1,000 messages, right? All of them will get that one message. It's a publish subscribe pattern. Clear so far? Yep, pretty simple. So now there is a variation of this pattern, which says, okay, I have something, but I really want only one of the subscribers to get. I don't want everybody to get, I just want one. The typical use case is I have a job to be done, and then I have multiple workers, but I want the job to go only to one worker. I don't care to which one. Whoever pulls the job first gets it, but I don't want the job to go to everybody because that kind of violates the semantics of what I want to achieve, right? So this one is called push-pull. So there is a one ventilator pushing a job, and then there is a number of workers which can pull it. Whoever pulls first gets it, and the job is taken, but only one will get it, right? And if multiple workers pull at the same time, one will be the one which gets it. And typical implementation in ZeroMQ and other queuing systems is round robin, which means you have a queue. So if I do pull, so client A does pull, client B does pull, and client C does pull, then if there is nothing to pull, they kind of block and wait. And then when the ventilator says, okay, I'm pushing something, I'm pushing the work into the queue, then whoever was first will get it. And then even like, let's say this one does it really, really fast and makes another pull request. Not pull request, but like pull. There is a time delay and there is another work being pushed. Even though it kind of says, yeah, pull, it will use a round robin setup, which means this request of pull will go actually at the end of the queue, such that these two guys will get the next item because they were before, right? So round robin means we have some sort of queue and we're going like round robin. So like one pool, another pool, another pool, another pool, another pool, another pool, another pool, and we kind of always go round robin, like we kind of go around the circle, right? Right, so that's another pattern. So in your particular problem, you're kind of thinking, okay, what sort of pattern do I need? Do I need this pattern or do I need this pattern? For lab 15, you pretty much need this one and this one. That's it. You don't need anything more complicated, right? It's just the most two basic patterns that you need to use. You don't need to think about anything more complicated than that. But as I said, there are more patterns to come. So this one is quite useful if you have to deal with jobs. And then you have additional variation on the first pattern. So reply permits only one exchange, right, at the time. So as I said, like if you have a slow server and you make a request and it takes very long time, everybody else waits for the request, right? So what you can do is you can use router dealer pattern, which is a bit more complicated, which carries ability to route a request like asynchronously. And that one allows you to have multiple things kind of happening concurrently, right? So for typical network setups and for typical multi-client situations, we usually use the router dealer pattern instead of request reply. So this one allows you to do more and allows you to do more logic with your behavior, right? So task 15 is solvable without this one. You only need the request reply and the publication, right? Because you want to notify, like when Bob types a message, it should go to everybody who listens to that particular room, to that particular channel. So this is a summary of like how they look like and what they sort of solve. And the patterns are well known, and the patterns is something that you pick, right? So who speaks to whom, in which order, and what you're doing with confirmations, and what are the guarantees. If you're designing any other networking stack or any other networking problem, you usually answered similar questions. So you sort of identifying who are the actors, who are the active components. Usually we give them names because then it's easier to identify who talks with whom and what the pattern is. And then you define like the direction, confirmations, and guarantees, and whether the work can be asynchronous or not. All right, so how hard is this? The easy parts are easy, right? So the request response is easy, and then broadcasting something to everybody who was subscribed to a particular room is easy. But it can get more complicated, as complicated as need be for a particular solution, right? So those are the very four basics patterns, but you can build much more complicated scenarios combining those patterns together. And then you can get arbitrary complexity out of this, right? So it depends on the nature of your problem and depends on the nature of the system, what patterns you will use and what you have to build. The building blocks are simple. Complexity can come from combining it. All right, so now a second topic, the data modeling. So in lab 15, you are kind of exposed to 0MQ, kind of a messaging patterns, messaging bus patterns or networking patterns, but you're also exposed to Redis, right? And with Redis, we kind of need to deal with data. We need to deal with who the users are, what the rooms are, and how the messages are routed to the users, right? So you know about SQL and you know about databases. And in database, the data is stored as tables. But Redis is sort of a data store, but it stores data in structures instead of SQL tables. And we often it maps really nicely to the way we store data in variables and in type system in your code, right? So in your code, you have to store data as well. And we usually have some sort of type system and some sort of very small data structures that we store data in. And those data structures typically are what? So if you were to store something in your code, you typically have something which is either a number or a string, right? So you say, yeah, I need to store a number or a string. And then you have a variable with a particular name, which creates a namespace for you and a particular type system, right? Because sometimes you don't want the number to be a number. Let's say you want a type which is age or something, right? Or price, right? So this is like a primitive level, right? Primitive. And then the second one is what? Sets, lists. And as I said here, if you have a name to get to somewhere, we have hashes, like hash sets, right? So those are the typical kind of low-level data structures that you deal in your code. And it's the same in databases, but in databases, you have those big tables. You have the rows and columns, and you have the cells. And what if you don't need a big table? All you need is a particular data structure which maps to this. Then Redis is what brings you from within your code, from within like your local scope of your program to something that can be shared across multiple entities, right? So we go from your single local compiled unit and saying, yeah, but it's so useful if I have a client and server to talk about the same things and share the same kind of concepts. So now Redis says, yeah, I can do it for you, right? So Redis stores named data structures. It's kind of like storing variables, and it has a very minimalistic type system, right? So it has the primitives. So here is a hash. It's kind of like a variable name, and this variable name has a value. And in this particular case, the counter visits has value 42, right? And the cool thing is with this counter visits, you can increment it. You can call inc, and you can say inc particular primitive thing, and it will actually make it to 43, right? It's very like programming. It's kind of the same as you're doing in your code, right? We have hash sets. So a hash set is a hash. It's kind of like a variable name again. And then it is a key value pairs, right? So we have a type, which is sort of like a record. And the record has key values, right? And the name, like the name of your variables is whatever that particular thing is. And as you've noticed, Redis uses this colon to define a human readable namespaces. So it's very easy because then it's kind of easy to read and easy to manipulate. But those are just strings. You can use arbitrary strings. It's just a convention that we're using this colon separated parts such that we can do certain search or certain like operations. Why do we have this 42? It means we have kind of a user type. So we have users and we say, we are talking here about the user ID 42, right? There's a bit of a coincidence between the visits and the user. It has nothing to do with one another. So then we have lists. And lists is kind of the same as the record. So this one is a record, but this one is a list, and we can push values onto the list. And then we have a list with a lot of values. It's like normally like a list. And then we have sets. So here is a key again, and we're saying add this value to that set, right? So we say, okay, we have this concept of a lobby, and the lobby has members, and the members is set, and the set has items. And then if we add something to the set, we will have more insight, right? And then we can invalidate. We can invalidate the keys. So we could say expire, and then we put the key. And then we say after 300 seconds, the particular session is like invalidated and deleted. So the choices what sort of data structures do you want to use? How do you model the rooms? How do you model the users? How do you model messages? And how you organize yourself, right? So the choice, all the choices that you're doing is the schema. And the schema is the model, and creating the model is what programming is, right? Choosing which code, like which method to use, is coding. That comes after, right? So as I explained, we have strings, scalar values, counter, like it can be string or it can be a number. We have hashes, like a record type. We have lists, sets, and we also have order sets. So we have something which is called zset, and the zset is kind of the same as here, but you don't, like, if you have a set, so if I have a set of members, and I have my some sort of a member set, and it's sort of like a set, and I said it's user 42, user 43, and user 1, right? It creates a set. There is no ordering, right? But sometimes you want to have some sort of ordering. So for example, if you say reading list, oh, list is kind of a bad name actually. So so I have to do, and then I have read, right? So now I have a set which creates, like, what should I read? And if I say, if I have some items, then they are in the set, and I can read the set and do something with the set. But maybe what I kind of would like to do is to order them, such that I order them in the priority list. So I say, this one is like really important, this one is not so important, and then these two are kind of not important either, right? So I kind of create an ordered list, and then I have a set, but the set has a certain order in which I can get items. So I can say, give me the top 3 items from my set, right? So it's kind of like a set, but it's more like a list, and it has kind of ordering built in, right? So you can say, okay, so then what's the difference between the list and the ordered set? There is no real, the difference is that the order set always, like when you inject things into the set, it kind of keeps the order correct, because you can inject things in random places. The list kind of allows you to add things at the top, at the end of the list, right? You don't have this kind of a flexible reordering done for you. You have to manage that yourself. So it's kind of a ranked collection for leaderboards or priority queues or like priority items to be done. Okay, so then we can represent, like for task 16, what you'll be doing today, you have to represent something. You're not doing today with Redis, by the way. You're just doing everything in code. But if you were to do it with Redis, you have 2 choices. You either represent a particular user as a record, or you represent a particular user as a collection of loosely coupled items, right? We talked about it last week. We talked about the array of structs and the struct of arrays. And this choice is very verbose here, right? These are not 2 syntaxes for the same thing. Those are kind of 2 different claims you're making about what constitutes a user. So in this case, you're saying there is a kind of a unit, and the unit has certain properties, but I'm treating it as a sort of encapsulated unit. The user is this encapsulated record, right? And in code, it's the same. You can say I have, typically you're doing it by saying I have a class, a struct, or you know, you say in Haskell, I have a particular data type, right? So those are all for this sort of a record. Sometimes there is a record. Some languages use like a record. So the other one is, no, I don't have this one thing. I have the collection of things which together, they form a particular user for me, right? So user 42. I need kind of this, but I can delete one. I can kind of do very kind of a loose operations. I can add something and so on, and it kind of creates a different claim. It's a loose collection of keys, right? Versus I have this kind of a combined record. So this data structures encodes the claim about the underlying concepts, right? So the concepts are different, and then the claim is the programming, and then the commands that you're using is the coding, right? To achieve the model that you want. So Redis is very common. It's a something that almost is difficult to not use. Every time you're doing anything with cloud or anytime you're doing something with network, it's excellent for caching. It's excellent for data sharing. It's excellent solution for a number of applications. And if you are doing Lab 15 and you think, what would I need to build to do Lab 15 without Redis? You'll realize how useful Redis is, right? It kind of brings all the machinery that you already have in your code kind of to the network level, and then you can kind of share it across your clients, right? It's like super useful. And all the major companies are using it for a number of different things. It has been in the market for a long time, and the concept has been duplicated in other libraries, which are Redis-like. So Redis is not like the only solution on the market, same as ZeroMQ. ZeroMQ actually is quite niche. Most people use a managed solution compared to ZeroMQ, but the patterns and the concepts are exactly the same. So your task 15 broker already uses the patterns from request, reply, and the publish, subscribe. And then an interesting thing happens, because if you're using Redis and you kill your clients, obviously, you know, like you have your broker, and then you have 3 clients, right? So Bob, Alice, and Charlie, they chatting, and then Bob goes off, and then Bob comes back, and everything works, right? The magic is, so this is a broker. The magic is you can actually kill the broker as well. You can kill the broker and restart it, and nothing changed for those guys. It like magically continues to work as if nothing happened, right? So if you try to build a system like this, robust like this yourself, you'll notice that ZeroMQ and Redis give you a lot of like value for not much effort, right? Okay, so we're not gonna do the reflections. You can reflect on it at home. So you can reflect how you're using ZeroMQ and how you're using Redis for Lab 15 or Task 15. And there are no wrong answers. Like you can build everything yourself. It's just a matter of choice. It's a matter of how you model it and the way how it feels after you've modeled it, right? If you model it right, everything will fall into place and everything will feel easy. You have this feeling, right? If you're programming something, you have a task to do, and like you're struggling, and suddenly you kind of something clicks and you say, oh no, I was doing it wrong. I have to do it this way. And suddenly like all the coding and everything kind of falls into place and everything feels easy. That's exactly what I'm talking about, right? So you're trying to find that easy model before you start coding, because you don't want to spend time coding the wrong model, which feels not right. So you're trying to find it, find the vocabulary, the semantics, and all the concepts such that when you actually have to code it, the code kind of writes itself, right? That's the goal. We almost never get there in the first iteration, but that's basically the goal. So next topic. How are we doing with time? Yeah, we're doing pretty good. So composition and decomposition. We talked about it last week. Object-oriented programming is great until it's not, right? So, and the difficult thing is that we, as an industry, we thought object-oriented programming is fantastic. It really solved a lot of things. It really offered a lot of really nice encapsulations. And what happened was, like, if this is a timeline, you know, in 70s, we thought, oh, it's like hard. then kind of OO happened, and we say, whoa, it's like fantastic. Like we should do everything using OO, right? And then for a long time, we've been doing OO, and we've been like, it's kind of like a, hype cycle. And we've been like, oh, it's like so fantastic. And then as time goes on, probably, I don't know, like kind of late 90s, early 2000s, we were kind of in the trough of this disillusionment, right? We like realized actually for large systems which need to change, which need to evolve, are always too restrictive. So always not bad. What always bad is to, as this slide shows, like you design everything works great, but you cannot predict what you're gonna need in the future. You cannot predict what the requirements are at that point of time. So you design everything here and it's great, but later in the future, some of your assumptions are kind of broken, and now you have to do something a little bit different, and then kind of get you to a point where you are paying the debt, right? So in this kind of a made-up example, we have merchants which were designed to be positive and kind of not negative, and you designed to have enemies which are the negative ones. But what later in the game, like after a couple of iterations, you say, actually, it would be so cool to have like a mischievous, like merchant, which are actually your enemies, right? Before all the merchants were your friends, suddenly you say, no, we kind of need this mischievous, like evil merchant, right? Because it adds an arc to our story. It adds an arc to the game. And then you sort of said, oh, shit. Now I'm kind of in this place where I have to have a merchant, which is kind of, bad, right? And you didn't plan for it. So then you have a little bit of a problem, right? So, I mean, you have to deal with it, right? And the way object-oriented programming kind of plans everything and deals with it is a little bit cumbersome. So for long maintained systems, we sort of realized after like late 90s, that OO is actually a little bit difficult because it's doing certain things certain way. So most languages which came, like programming languages which came after, and most of the conceptualizations which came after, they said, actually, let's keep all the good stuff from OO, but let's kill one thing that makes this bad, right? And what is the feature that makes this bad? Inheritance, right? So the is a hierarchy breaks when the entity kind of needs to combine traits which you didn't plan in advance, right? You actually have to have a foresight long into the future and say, this is a relationship will always hold, right? And you don't know, you cannot tell that it will always work. So we cannot use this hierarchy of is-as relationship. We need something else. And the something else is this composition. So instead of inheritance, we said, okay, that is risky. Like inheritance is risky because we have to predict how things is a relationship will hold 10 years from now, where I don't really know what's going to happen next year, right? So then we say, okay, that's a bit risky. So let's replace it with composition. Composition is much better because I don't need to predict anything into the future. I can compose things in a new way later, right? I just have a lot of things and I compose them certain way today, but tomorrow or 10 years from now, I can compose them differently. And I don't need to change my model because the things I'm composing are already designed, right? So when you describe an entity, you kind of have a subclass hierarchy because you're saying I have is a relationship, right? Here you're saying has. So this one is a relationship. This one says has certain traits or certain property. That's why we went to traits and things like this, right? And then when you need to add a capability, Well, it's a little bit like difficult. And here you attach new capabilities. And then if you need to remove something, you have to completely redesign your hierarchy. You have to go back to your drawing board and say, okay, actually that has changed, which influenced everything. And then you have to redesign everything, recompile everything, and so on. It's like a major undertaking. Here, no, you just like remove a component from a running system. So ECS is much more versatile and kind of modern programming languages, including Rust, Golang. They sort of said, yeah, inheritance is a little bit risky. Let's not use it. Let's use composition instead. So, if you have a hostile merchant, no problem. You attach combat to the merchant and you remove peaceful traits and you're done, right? You don't have to change all your modeling. You don't need to change your world. You not need to change who is who and so on. It's like easy. So no class hierarchy needs to be modified. It's kind of a much more easier maintenance wise, right? So what is this ECS? It's a kind of a notion of changing the way we model and compose and decompose things. The entity is nothing more just an ID. Entity in itself is nothing. It's just like an identifier of what capabilities it has. And then the capabilities are components. So it's just pure data. There is no behavior. There is nothing. It's just pure state. And then system are functions. So functions are kind of systems which combine entity, which is just an ID, with the data and with the behavior, right? So we sort of isolated those three individual things separate, and then we kind of combine it. And again, if you look at the big picture, before all happened, we had kind of like a functional and procedural programming. And we were kind of using it. Then we went to the OO and we said, oh yeah, that was so great to combine this into this polymorphic, entities, and it kind of gave a lot of power to have the objects and classes and so on. And then there was this disillusionment with the is-a, but we've learned how to do this in a better way, such that kind of now when we do ECS, we kind of know, like, we kind of go back to kind of a lot of functional feel, but we're not doing the same naive ways as we did before. We kind of learned our lessons. So modern functional programming and Rust, for example, they kind of are doing it in a different way than, the procedural languages were doing like in 70s and 80s, right? And ECS is kind of a very nice metaphor to use most of the time. Most of the time, you would benefit if you model your things in ECS way. So entities don't do anything. It's just the IDs. Systems do things with entities, right? So the inversion is, it's a little bit tricky if the first programming language that you've learned is object-oriented, because now it's kind of the same, but like upside down, like it flipped, right? So lab 16 or task 16, you're gonna endeavor in a moment. You have a player. You have the player position, where the player is. You have inventory, what the player has. And then you have a certain paths on the map where the player can go and what is blocked and what is needed to pass from one area to another. And then you have items which can be put into inventory, and you have NPCs, right? And then you sort of have this SQL-like table, but the thing is you don't need to fill in the empty things. The only thing you care is the ones which actually make sense, right? So you have your entities, you have your data. So the entities are this. The data is what can be generated from the from the entities, and then the system just plugs things together, right? So it's all about combining it and making it sort of logically cohesive. So you're not gonna use Bevy. Bevy is a Rust game library for doing ECS. So today we're not using Baby, but Baby is for lab 17, for task 17. So 16 is ECS by hand, manual, easy, small. And then if your game grows and you kind of outgrow what you're doing manually, that's 17 ECS again, but with Baby, right? Okay, I don't have screenshots. I will have screenshots after today. So we are done with the ECS system. Do you have questions for ECS? Who knew about ECS before? Okay, so great. You're gonna learn some new ways of doing things. Is it very different to what we've been doing so far? Not really. You will realize by doing the task today that it's like, yeah, it's sort of programming as usual. It's just that you will have a bit of a conceptual oversight of like why things are the way they are. So a little bit about task 16 and you doing ECS. You don't have to think about ECS. All those concepts that I kind of introduced today, those are just names. So those are just names. Like we've done everything already. We just were kind of not naming it that way, right? So you just have to implement a couple of functions and the ECS is already prepared for you. Like the setup is already there. You just need to hook up some logic, right? So domain-specific languages. As I said, you were exposed to domain-specific languages all your life, like SQL, CSS, HTML, JSON. All those languages are designed for certain things and they have certain capabilities, right? So SQL is great because SQL kind of compresses what would take you like a page of Golang code to express, and you can express it in a very concise, very like one-liner, right? CSS is the same as like the language for modeling the manipulation of styles and so on. Regex, have you used the regex? I hope Christopher forces you to use regex a little bit in cloud possibly. Make files, how many of you are using make files or configuration files, Maven and things like that? All those are kind of domain-specific languages. You're expressing something, you're expressing your intent in a particular language, and then there is a parser which parses that, code, but those are not programs, right? Makefile is not a program, it's not a programming language, but it is a domain-specific language, right? Shader programs are quite cool because shader programs kind of they look a little bit like programming languages, but they are domain-specific languages as well. There is a lot of vocabulary, a lot of like unique things that is specific to shaders. You're gonna learn about it like next year. So why we have them? Well, we have those general purpose languages. So like we have this class of general purpose languages, and like Python or Haskell and so on, C, but they are kind of really big, right? What if you are just kind of you only want to express things about building, like build systems, right? Like it's a very tiny domain. And then if you have to do everything you want using this very generic programming language, it's like, yeah, this is like trying to use like a cross-continental container ship to carry a single banana, right? I mean, to carry a single banana, you can just walk, right? You don't need like the massive container ship, right? This is like this massive container ship. And here is like, okay, there is a very tiny language, which is called make file, make, and it has like a very tiny syntax, and then you can express everything you want, right? So that's why we have DSLs. And that's why we have DSL for SQL, for example, because we don't want to express queries in C all the time. That would be super tedious, right? So Haskell, lab 16. You have in lab 16, task 16, you have a 3x3 grid. And you have certain areas. The areas have names. And the areas have names as on this diagram. I know this one is cave. I don't remember if highlands is this one or this one, so I will not say, but basically all of them have names and they are kind of connected, right? So cave is connected to highlands via a river. And I believe it's this one. So this one is highlands, and there is a river, right? So this one here is an ocean. This one is an ocean. And this one is a river. And cave is connected to highlands by a river. And this kind of word defines it, right? And it says to cross from cave to highlands, you need a canoe, right? So to go from here to here, you need to have a canoe. The player needs to have a canoe. So we have kind of a domain-specific language, which is specific for Lab 16, and it defines the world, and it uses certain words. It uses the word world, area, connects, via, requiring, contains, area, and then it defines the win condition, right? All of this is defined in Haskell. And all of this, if you kind of read it, reads like a DSL, right? So it reads like a domain-specific language, but it actually is all pure Haskell, right? There is nothing outside of Haskell. But for you to understand, you need to know Haskell, right? And then you know, oh, yeah, I can kind of see this is a function which takes all of this as a parameter, and then those are functions, and then take those parameters, and then I have some sort of functional composition, right, happening. So you can read this because you know Haskell, but for somebody who never saw Haskell, that will feel like a makefile. That would feel like some sort of DSL, right? But it is not DSL. It's Haskell. So we are kind of here. It is Haskell. But for task 16, we defined kind of a subset. We defined a very small language that has those things. So we defined certain vocabulary, and we kind of created a DSL for ourselves, right? But to use this DSL for ourselves for this particular lab, unfortunately, you need to know Haskell, right? There is no way around it, right? So if we do a different language, if we say, okay, we have a different language. We don't like Haskell. We like brackets and curly braces and semicolons. We have this language. So we have area cave, which connects highlands via river, requires canoe, and blah, 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 right? We have our own language now. It's not Haskell anymore, but we need a parser and we need some sort of processor for that language to create the word for us, right? So this is lab 17, task 17. So internal, the parser is for free. The type checking is for free. Everything is for free in this case, but you need to know Haskell. In this case, if the language is external, a person who deals with this, your game designers, they don't need to know Haskell anymore. Like all they need to know is this language only, right? They, like you say, if you know this language, you can design new levels for me, right? So what DSL is composed of? Yep. Yep. We can have a break. Yep, let's have a break. 10 minutes?
The SharePoint slides for Monday on the presentation that we are supposed to present for Studio Programmable.
Okay.
Could you share them?
Sure. Yeah. Yeah. I can do that. Yeah. Right. So we got to the point where we motivated having a domain-specific language is a good thing, and we motivated that even if we are not defining kind of even if we are not doing the external DSL, we always try to make the internal as cohesive and as easy to use and as kind of nice, such that the code kind of codes itself, right? So even if we're not doing the external one, we still, whether we are aware of it or not, we are defining a language which the programmer, which is us or others, have to use to kind of code certain behaviors, right? So we always doing it. So the most visible is the concrete syntax. So what the source code looks like. And then what's not visible is what this gets converted into, right? And this is also something that we kind of discussing in this class. We're saying programming happens on this level, and then converting from this level to here is what is called coding, right? So coding is you go from here to here. That's coding. But you can program exclusively here. And as you gain more experience and as you gain more insights into different programming languages, your thinking will kind of shift from here to here. And then you will observe that you can solve certain things here, but then a concrete syntax does not allow you to express it. Like, you would say, I could solve it like this, but in Golang, I can't, right? And then you say, yeah, the Golang is the limitation, right? So concrete syntax and the abstract syntax. This one happens in your head most of the time, but we formalize it as well. We have abstract syntax representations, which we use, and then we have the concrete user-facing syntax that we expose. So one of the interesting kind of takeaways is if you have a compiler. So if you have a compiler, the compiler has its own internal representation. So the compiler has a certain, let's call it virtual machine inside the compiler, which uses to represent what you're doing, right? And then on the front end, so this is called the front. On the front, you can have C, you can have C++, you can have Rust, right? And the compiler takes those and converts them into this, right? And you could say, okay, like this one must be more abstract to what those have, right? Because they have certain representations and they have certain abstract representations from concrete syntax. There is a concrete syntax of Rust, and there is like the Rust abstract representation and so on. And then you have this kind of traversals to the internal representation of LLVM, for example, right? So LLVM is the low-level virtual machine, which is basically the internal representation of what happens on the front end. And then the compiler has a backend. And the backend is, ARM64, for example. It's a particular computer architecture, right? And then this representation, this abstraction has to get converted to here. So there is another step. So there is like one step going from concrete syntax to here, from here to here, from here to here, right? And you, as a professional, it would be very desirable if you don't have to know all the details, of course, like all the low-level details of how it happens, but at least you kind of understand and you feel the concepts of what happens here and what happens later here. What is cache? What is a memory barrier? Like we often talk, like in C++, we talked about the sequential memory barriers. And it's like, what is this? It has nothing to do with the abstract thing, nothing to do here. It's like it traverses all the way to kind of a CPU, and then we kind of specifying something which has effect over here, right? You get the idea? You get this sort of hierarchy? And it is quite complicated, and like we don't know everything, but it is always a kind of a tower, right? So here we have a tower with going from concrete syntax to the abstract model. And then we usually express this abstract model in some form of syntax as well, because we have to write it down. It cannot live in our head in like a random thoughts. It has to have some sort of language. It has to have syntax, right? So there is a concrete syntax, which is a syntax. There is abstract model, which is also a syntax. And then there is a static semantics, which reads this one and says, okay, there is something wrong. Like it checks if this one is consistent and if everything here kind of compiles, right? And then if everything compiles, we try to run it, and then we have runtime problems, right? So then we have runtime exceptions because it compiled, it kind of makes sense, but the combination of things during runtime didn't make sense, right? And we cannot check that. We can do some dynamic semantics analysis statically by the compiler, but not everything can be checked. There's certain race conditions, certain things cannot be predicted, right? So we kind of go there. So this is a very simplified model with 4 layers, but like when you're typing your code, you're navigating consciously or not all those 4 layers, right? So when you're typing concrete syntax, you usually coding, so usually converting what you came up with, like I need a certain type with certain properties, so then you code it. So you go from the abstraction, which is the model, to the concrete syntax, and then the compiler checks if the syntax is correct, and then you can run it. In this case, we kind of using this one to check if the abstract model, like when we're designing this, we have to check if our abstract model is correct by doing static and dynamic semantic analysis. So if you have a DSL, which is very very immature or kind of difficult to use, it's sort of like at the bottom. So somebody came up with a syntax. I said, oh yeah, I have this JSON schema, right? And then that's great, but like what does it mean? Well, like what the keywords in your JSON schema actually mean, right? You have to have a meaning attached to it. If you only have the schema, that's not enough. You have to have the abstract model and the semantics of like what those keywords mean. If you said person and name, what does that mean? Is the name full name or is it just the surname? Like what do you want, right? What is the meaning behind your symbols? So there, static semantics is specification errors, like what properties we should have for our implementation, for our modeling. So in our case, in the task, as I said, like I deleted this thing, but we have those areas, right? So we have those 9 areas. And we operate within those 9 areas. And then when we're designing language for our world, we have certain questions like we say all identifiers for the areas have to be unique, because if I have area called cave and I have another area called cave, I'm in trouble because I cannot distinguish which one is which, right? So there is certain implied things like they have to be unique. The connection must only reference 2 areas, because the connections always connect 2 things. Like there is no connection which connects 3 things or just 1 thing. Like all the connections connect 2 things, right? So and so on. So that you have a kind of a set of constraints, set of things that make sense. And those things that make sense are in your head. And usually you say, yeah, of course, it's obvious, right? But you have to express it. Like you actually have to express it that it's there in the syntax, right? So those are the ones I've done for you. Like you don't have to do it yourself. All of those are done for you already. So the DSL, if you do it wrong, will kind of allow you to do things which are wrong by design, right? And that's the worst case scenario, and that's where most of our bugs comes from. We basically allowed something to be correct, the compiler takes it, but then it sort of does not make sense. So if if you have to do if checks, if you have to do unwraps, if you have to check for conditions in your Rust code, that means you didn't design your DSL correctly. You didn't design all your functions and things properly because you have all those edge cases. Like if you designed it correctly, you wouldn't, right? So you're trying to make your design complete such that the compiler is your friend and the compiler kind of enforces certain things for you. So, for example, are the crafted items consumed or reusable? Like, you have to design it on the level of the model, and then in the code, if the items are not consumed, they will never be able to be consumed. You don't have to do if check because the model enforces what you said it should happen, right? So if the domain experts reads your spec, reads your code, but cannot answer all those questions, then the semantics is missing. So here is an example. We are designing kind of a new language for expressing this world, right? And we said, yeah, yes, let's use this Tom's obvious modeling language because it's super simple. And we say we have a world. The world starts with a cave. The win area is Thornspine, and then you have to get there, and you have to have a healing potion to win, right? And then there are connections. So there is a connection between cave and highlands and between cave and nowhere. And then everything is string. Everything is strings, and like nowhere and flamingo are not defined anywhere. So, you know, it reads, it doesn't complain, but it will fail at runtime because we did not define nowhere and flamingo, right? There is no definition of nowhere and flamingo in our world, so it will fail, right? Here we defined the world using a typed DSL with a type system, and we defined what the connection is, that it's either free or blocked, and the word has a start, a connection, win area, and win item, and then everything is typed. Nowhere and flamingo are not defined, but highlights and cave are not defined here yet neither, but you will have to define them by defining the area. So if the area is not defined to contain nowhere, then it will not compile, right? So if I have if I have this, and then I'm saying, like in my code somewhere, I cannot put a string which says nowhere, because the compiler will complain, will say, I need an area, and you need to define the area, and the area needs to have nowhere as one of the DSL, like one of the ADTs, right? So somewhere in your code, you have to define data area, and you have to say it's like cave blah 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 / nowhere, right? If you don't have this line, then you cannot use nowhere because the compiler will say, yeah, I don't know what you mean by nowhere. Like nowhere is not the area. But if you have your area defined and you define your ADT, then it's fine, right? So in Rust, we're using enum. So we're using enum for ADTs. In Haskell, we were using data. The ADTs were kind of using a data keyword. So it's the same with behaviors, but we're not gonna go with the behaviors. We could. So here again, we have strings. The strings can be anything. Here we have behaviors. Like the behavior here is like patrol is a string, but the behavior here, which says is a patrolling area, it's defined on the type system level, and it enforces that I cannot have behaviors which are not patrol, follow, or guard until. I have 3 behaviors, and if I try to use something like here, like florping, it's like, I don't know what florping is. You have not defined it, right? If you declare it as define it as a string, it can be anything, but here it cannot. So the power of ADTs is that the compiler become like really your friend, and the compiler will tell you that you're doing something wrong, right? Yeah, so we don't need to go there. We don't need to do the parser because that's task 17 and 18, so we can postpone it. So the solving all the modeling challenges and conceptualizing what you need to program is the programming part, and it's the fun part. Coding it into the particular language, it's mechanical, and that's the part which is by majority of the progress taken up by generative AI. So generative AI can do most of the coding for you instead of you doing it, right? There is a nice talk. I will put the talk onto the lecture slides as well. So there is this guy. Let's see. YouTube coding is not software. Jeremy Howard. Yeah. Oh, come on. This one. It literally. So he's kind of a guy behind the transformer architecture. So he is really deep into the whole generative AI, and he distinguishes coding from programming as well. But he also admits that these days he does not write code majority of the time himself because the models are good enough for writing code. So he in the interview, he says he writes code about 10% of the time. The rest of the time he is doing programming, but he does not type code into the editor. The AI is typing code into the editor. And the talk is very good. Like it is quite hard. Like he's really into things. So it's kind of a mentally demanding talk, but I will put the link and you can watch it. It's yeah, it's almost 1.5 hours, so it's a bit long, but it's worth spending time and like listening to what he has to say, because he really understands internals and what are the strengths and what are the weaknesses of generative AI, and what you can use it for and what you cannot use it for, right? So it's quite good. All right, so let's finish this. Let's finish the lecture. So Haskell is really good for DSL prototyping because it gives you all the easiness of defining your own syntax, because everything is just functions. And you can have like a mini DSL because you just can. With Rust has a specific syntax, and doing DSL requires you to write a parser because you don't really want to deal with all the extra notations and extra things that Rust enforces you to have. So Haskell makes an explicit at the beginning because everything is kind of already in there. Pattern matching, functions, and ADTs, sort of like when you define your ADTs, it's kind of like defining grammar in EBNF notation, and then the rest sort of follows. So it is super easy. You may want to do your own DSL based on your own syntax, but then you have to write your parser. If you benefit from a parser that already exists, like for example for TOML or for JSON, then you have to build the machinery on top to enforce the type system on top of that, right? So, you know, this really reads like a BNF notation. If you never heard of BNF or eBNF, then look it up. It's a notation for expressing grammars, and this kind of reads like BNF. Like you're expressing a grammar for what is an area and what is an item. And the area is cave, highlands, blah, blah, blah. And the item can be axe, rope, blah, 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 right? And then the connection, if it is between area and it's free, there is no blockage. But if there is a connection between area and it's blocked, then you need to carry an item. And this logic is like very succinctly expressed here in Haskell. In task 16, it is very succinctly and very correctly expressed in Rust for you as well, right? So when you check task 16, you'll see, oh yeah, it's kind of, it is doing that, right? And why it is doing that? Why we defined it like this? Why we didn't say, okay, area is some sort of a container which has strings and cave is a string, because then we would have a lot of problems, right? We would have a lot of semantics and dynamic semantics problems. Here, the compiler is our friend, and the compiler enforces that things are defined properly, right? If I write a connection function in Haskell and I miss some of the areas, what the compiler will tell me? The compiler will tell me your pattern matching is not complete. You missed some of the patterns, right? So the compiler will tell me when I'm having implemented something, right? If you treat everything as strings and you forgot some if statement somewhere, the compiler cannot help you with this, right? All right, so then you can do the systems. You can do invariants by functions which enforce certain things. So you can, for example, have a function which checks if given your inventory and a particular connection, whether you can cross from one area to another, right? You can write function like this because you have the concept of inventory. You remember entity, components, and systems. So components are my items and my connections. And now the system is this can cross function, right? And then I can kind of check, I can do certain invariants about the world. And then I can combine them into a list comprehension to make sure that everything in my world is consistent, right? I can kind of express it in the very concise and very easy syntax. I mean, again, in the Rust, you have that done in Rust. Here I'm using Haskell because I hope you can read Haskell, and it's a little bit more concise. It fits more on the single slide, right? So I defined my world. I defined my systems, like what constraints can I express, and then I actually defined a check if my world is consistent by having kind of a list comprehensions which go over the constraints that I had over my entities, over the components of my entities. So the Haskell prototype answers one question: does the design work, right? And if the compiler is happy, like I have not implemented any game logic yet. I'm just kind of implemented all the invariants and all the moving parts. I kind of defined the language and I compiled it. I didn't like build the game yet, but the compiler already says, yep, the design works. The design is coherent and it has all the invariants kind of successful, right? The types fit together. The evaluation handles every case. I didn't miss anything. And the language is expressive enough because I can express all those constraints, right? So if you were to do it separate, you would kind of do it in Haskell first. And once you are happy with it, then you would implement your own language, your own parser, and your own Rust types, and your own kind of a baby system, right? So you can do it later. But this is easier for prototyping. The prototyping is not throwaway. You can change your design and reevaluate. And you have this prototype as a kind of artifact that you can play with later. All right, so this is lab 17. This is actually lab 18. 17 is simpler than this. So at each level, you're doing kind of some symbolic choices, and you're checking what socket patterns do I need to use? What Redis types do I need to use? Is it a set or is it a list? Is it like an order set? You are thinking what becomes a component, what is your data, and what is the behavior, what becomes a system, and what continues to be a component. What concepts belong to DSL and what concepts you don't want there. And then what can be checked just from analyzing the static structures, what is the static semantics, and what needs to be checked on the fly online with the dynamic semantics. What does it mean to evaluate? What does it mean to run something, right? All right, so yeah, like this is a bit personal. Like the joy of programming for me is finding the correct representations. That's the joy I have. And I have to admit, generative AI made that joy even stronger, because before I had to find those representations and then code them. And now I can find them and AI can code for me, right? So I don't have to spend my time on the coding part. I think from my experience, the AI is not really good at this. It cannot navigate those hierarchies of abstractions, and it connects different abstractions properly. It kind of operates really well on this one transition from the last abstraction level to the code, to the syntax, concrete syntax. But even there, like it cannot navigate, like it's sort of, let's say you are doing something and you want it to be aware of what happens here and what happens here about, for example, cache lines. It doesn't know that, like it does not have a model because it is trained on like source code, it's trained on language, and the language does not have the abstraction layer, which it kind of was used to generate that language, right? So this abstraction sits somewhere which is not accessible to LLM to be trained on, at least not yet. So it kind of knows everything about this, but does not know too much about this. Inferring like what your abstractions are this way is much harder. Like this is sort of much harder to do. And the good example is I can give you a piece of code and I can ask you like, name me, like you will have it in the exam, like name what this function is, and you will have to do this way. And it's like kind of hard like to do because there are like infinite possibilities of what that, like whoever wrote that code, what their mental model was, right? What they were actually doing. So going this way is like always kind of like almost always one way. And this way is much harder. So LLMs are kind of not great at this and they cannot navigate this. There is a master student who is working with me, working on generative AI, generating code which takes cache cohesiveness and cache lines into account. And we don't know the results yet because he's doing his project, so we will know the results like in December. But that's kind of the area which is sort of cutting edge, and we feel that LLMs are not that good navigating the hierarchy, right? All right, so tasks 17, 18, and 19. The whole point about those tasks is the representation. I don't care if your game works or not. I actually don't really care. What I care is how you made it to work, how you made your models such that the code followed, right? I can check your code, but like all the tasks say, don't like generate the code by AI. The generating of the code by AI is fine. But you cannot generate the abstractions correctly with AI. The AI will make wrong decisions, especially with task 19. Because we're using Bevy, Bevy is a very moving target. AI also has a bit of trouble with Bevy. So you will have to check the documentation probably sometime yourself and do a little bit of coding, maybe yourself. But I'm hoping you can generate most of the things using generative AI. And those tasks are programming heavy. They are heavy in the conceptual part. All right, so that's it. We'll have like a very short break for those who want, and then I will push the task 16. And what's gonna happen? You're gonna read it. The task 16 is individual, so no group work, but you can ask me questions. Discussing like openly with the class is fine. So you can ask me questions if something is unclear. Most of the scaffolding and most of the boring parts are already there. And most of the nice things related to modeling the world is already there as well. So you are giving the world, you are giving a lot of scaffolding, and there is a little bit of missing logic. The missing logic, which is missing, it's a little bit hard to predict how much you can do in 2 hours, right? So I was trying to scope it in such a way that you can do it all, but I don't expect everybody to do it all, right? So pick your battles. Pick which missing logic you want to focus on and do it first, and then next one and next one, okay? Just by, yeah, so I will stop recording.